Okay, we'll go ahead and begin. Welcome to all of you for joining us today. My name is Scott Coughlin. I manage eminformation.com, which is hosting this webinar, the first in a series of occasional webinars to be hosted or co-hosted by EMInfo. I'm assisted by Kim Deep, who's helping with the webinar controls today behind the scenes. Thank you, Kim. This webinar will run 60 minutes. As you know, our presenters are Brett Alger of NOAA, Mark Hager of the Gulf of Maine Research Institute, and Farron Wallace, also of NOAA. They can each fill out their details for you a bit more during their remarks. And by the way, we'll also provide their contact info to you as we wrap up today. We've allowed 15 to 20 minutes toward the end today for questions, so please don't be shy about helping us make good use of that time. Just use the on-screen box to send across your thoughts or questions. We'll hear from all three presenters and then take up those questions. If you would be so good as indicating your question, who you're addressing it to, that would be great. And if it's up for grabs, that's fine too. So with that, thank you again for joining us, and I'll turn it over to our first presenter, Brett Alger.
Thanks, Scott. I guess maybe just a real quick sound check and screen check.
Sound good?
All right. Well, thank you, Scott. Thank you, Kim, for setting this up and inviting me. And also thank you to Mark and Farron as co-presenters on this webinar. What I'm going to do to kick us off is just sort of set the stage of what's going on in the United States in terms of electronic monitoring development and implementation. Talk about some of the successes, some of the challenges, and then at the end really bring us down to introducing some of what Farron and Mark are going to focus on, which is some of the technology and the applications around AI and machine learning and sort of what they've learned in their programs and how they're taking those lessons and moving their projects and their programs forward in this space. And hopefully through this webinar, we can have a really good dialogue and exchange so that people can continue to explore this space in support of electronic monitoring. Just to sort of set the stage of what we mean when we talk about electronic monitoring, because people certainly have different vocabulary on the technology, but effectively what I'm describing here is what you're going to see on most vessels and most fisheries in the U.S. and even the world, which is a system that has a series of cameras placed on the vessel, typically 2 to 4 cameras, sometimes more, sometimes less, a GPS receiver, a series sometimes of different sensors, hydraulic and drum rotation sensors, all controlled typically in the wheelhouse by an EM control center that is, collecting all of the information, the imagery, the sensor data in the wheelhouse of the vessel. And then downstream of that, that information is retrieved off the vessel and then, provided for video review or analysis or summarization and different processes to then provide that information to managers and scientists for the fishery. In the United States, we have a number of programs that have been implemented, which you're going to see in bold lettering. We have a number of programs that are what I would call in a pre-implementation phase. Either they're being developed under some type of exempted fishing permit or they're being considered by the respective Fishery Management Council. Or there's instances where the programs are in a pilot phase, and those are denoted in italics here on the screen. And I should maybe make a quick note that this is the unveiling of this map. So bear with me if it's not as readable on a PowerPoint slide as maybe it would be in a document. But if we go around the country, we look up in the upper left of the screen, we see in Alaska we have a number of programs that have been implemented. And a couple that are going to be coming online hopefully in the next few years. They're in a kind of a pre-implementation phase. And just to maybe pause, this will be the region and the set of programs that Farron will be talking about in a little bit. We move down the coast to the West Coast. We have a couple of programs that we just put into regulation. and then a couple that'll be following on that will be going into regulation hopefully in the next year or so, and then a pilot project. Pacific Islands, we have a program that's underway. In the Southeast, we have a snapper grouper project. The Atlantic highly migratory species has a program that's been implemented since 2015. That fishery is actually prosecuted all the way from Maine to Texas. So even though you see the label there down by South Carolina and Georgia, it's actually a fishery that expands quite a large distance. And then in the Northeast, we have some projects that are underway in sort of a pre-implementation phase in Northeast multi-species and herring and mackerel, but also a couple of new pilots that are underway in the for-hire fishery and in the scallop fishery. The only thing I want to maybe close with on this slide is just to make a point that, as you can see, we have quite a diverse set of projects and programs, a range of different types of species, including now a non-fin fish in terms of scallops. We have a range of gear types, a range in sizes of vessels, and that's a long-winded way of saying that we have quite a bit happening in the EM space, and it's quite diverse. And so I would close by saying that, you know, I would argue that EM is possible as a data collection tool in almost any fishery that you can imagine. And then just lastly, before I leave this screen, is just to point out that when Mark Hager is going to be presenting, he'll be talking about the programs in the upper right there, the groundfish fishery in the Northeast. In terms of how electronic monitoring is used, the different applications, what you have in front of you is, I would say, a mix of realized applications and then maybe a mix of sort of theoretical or conceptual applications. But I'll walk through just some just high-level notes about, you know, how EM could be used, right? We can collect information to support our science and our stock assessments, develop information on bycatch, and perhaps do some ecosystem research. We or programs are using a lot sort of in the management space in terms of monitoring either vessel level quotas or groups of quotas and sector quotas. And there's also applications where the EM is auditing the logbook that comes from the captain or the vessel that's reporting. It can certainly be used to verify retention of catch in certain sort of, max retention, full retention, optimized retention type fisheries. You can certainly monitor fishing if you wanted to allow access to people fishing or transiting through closed areas, and certainly provides increased accountability overall. And then lastly, these are a little bit more theoretical, but I do think they're possible. Is there's possible applications of using EM in terms of sustainability certifications, improved traceability, in value-added products such as publishing or displaying that the fish are EM caught, if you will. EM is not without its challenges. Certainly, I've listed here in sort of some broad categories. Cameras can struggle to identify certain species or get weight or length information, and they do require that you think about how you handle the catch on the vessel maybe differently than you would have traditionally. How do you transmit, review, and store the video, which I alluded to at the beginning? How do you write regulations for technologies that are changing? How do you stand up EM on sometimes older data infrastructure? Some of the analytical challenges in terms of how do you develop EM standards and compare new data with information collected from older systems. There's a big need to resolve a lot of the policy issues in terms of how do you pay for the program, how long do you retain the video, who has access, who owns and the video, and some of the privacy issues. I would argue that some of the policy issues are the biggest sticking points or challenges to resolve for EM. And then lastly, certainly a lot of education and outreach that is needed in EM. And the bottom term that I use there is scope creep, the idea that you've created the program for one reason with certain expectations and agreements with your fishing industry, but perhaps those start to change and you need to resolve those. But I'll just stop and just revert back to the second line there. And what I'm going to focus on and what you hear from Farron and Mark is, a lot of what's happening in the machine learning, the computer vision, and the AI space, I think is really, for the most part, not entirely, but for the most part, targeting the cost and logistics of EM programs, the transmission, the review, and the storage of the video. This is a slide that I've shown in a number of presentations I've given in the past. I've added onto it a little bit. The idea here is that the video comes off the vessel on a hard drive, either picked up by a person or sent through the mail by the captain. transmitted to a computer somewhere, and eventually somebody sits down and reviews the video, effectively looking over the shoulder of the people on deck. And so what you would see here is what you're going to see in most programs, the idea that people are handling catch, they're collecting information, and so the person reviewing the video is sitting somewhere a distance away trying to collect the information that they can, which proves very costly. And then, of course, downstream from there, you're storing all of that information. As I mentioned, the costs between transmission, review, and storage in many or most programs, these three pieces are probably half or more of the cost of the entire EM program, which, of course, makes it very difficult to then implement if you have such high cost to a program that is desired or driving to reduce cost of data collection. In terms of the video review space currently, I think most of the review is done by humans, most or all of it. I think the next bullet down is probably where we see another large endeavor, at least in the US, is to try and reduce even the human video review in terms of the portions of video. So, could you review 20% of the trips, 20% of the hauls, 20% of the catch? But then the last two bullets, the larger bullets that you see there, I think we're going to hear from Farron and Mark on, is some of the computer-assisted human review, or even entirely or mostly computer review. And I should qualify that I came up with these terms a little bit on my own. These might not be the exact bins that Farron, Mark, or others would put them in, but the idea here is you're trying to process information faster. So review only the fishing events, or can the computer ID flatfish versus roundfish, or can it even start to collect length and weight and other types of information in a more automated fashion? And so just to hit home really quickly, back to the slide I just showed you, I think a lot of what this work is striving to do is, reduce the cost in terms of transmission and getting the video directly to the, the onshore, processing person or facility, whatever you would want to call it, and then focus the actual data collection on, the data you want to specifically collect in terms of this case, the length of a fish, and reduce or eliminate a lot of the other ancillary data that's collected. And of course, downstream of that, you're reducing your storage costs. With that, I just want to take a moment and say a quick thank you and a plug to some upcoming opportunities for discussing EM and machine learning. NOAA is going to be hosting a couple of workshops, one of which is in the fall in New Hampshire, the other one in Seattle, Washington in early 2020. I am a co-chair to an ICES working group that was just developed to work on EM and machine learning and other, fisheries-dependent data collection programs and applications. And then lastly, a to be determined, but NOAA will be hosting a machine learning workshop across a range of disciplines early in 2020. So after the webinar here, certainly reach out to me or others within NOAA with questions on these opportunities. Just then a real quick introduction. First up, we're going to hear from Farron Wallace on e-monitoring in Alaska, on a couple of different fisheries and therefore different applications of how they've been working with the University of Washington and other partners. And just a quick note, if you would have saw at the beginning, Farron is now located in Texas at our Galveston lab, but he leaves behind a tremendous amount of work and expertise. So thank you, Farron. And then we're also going to hear from Mark Hager, who's been working in New England on a number of fisheries and for a number of years. And he's going to talk about the development of EM and machine learning applications in the New England groundfish fishery. And this is just probably a quick note to point out that at one time I did sort of kind of help Mark do an EM installation on a vessel. So thank you, Mark, for joining as well. With that, I am going to kick it over to Farron.
Okay, thank you, Brett, for the introduction. Today I'm going to talk about innovative monitoring, and all the work I'm going to present today is made possible through EMIP, which is the Electronic Monitoring Innovation Program. This is a collaboration between Alaska Fisheries Science Center and the University of Washington. The goal for us is to develop machine vision, And what machine vision is developing remote monitoring systems that support the latest developments in machine learning, also known as artificial intelligence, to improve system functionality, reliability, and improve the timeliness of data. And we're trying to provide an end-to-end solution so you have a fully automated computer system sending data back, transmitting data back to our servers here. So this is a system that can see, learn, process, and transmit data. And I think we're fairly close in some of our tools, obviously much farther away in other tools. First, I thought I'd talk about the machine learning development cycle and what it takes to develop machine learning. And certainly in most situations, you start with a monitoring system. This could be a new proof of concept system, which what we were working with, machine vision cameras. They get deployed to the fishery. You collect your imagery and your sensor data, and then you bring that data back and you use it to annotate all of the images. So anytime a fish is caught, for example, you draw a box around the fish and put what species it is. And then through time, you collect enough imagery where you can train the detector, the machine learning detector. And then you repeat this process several times. You have to do each of these cycles, do a lot of quality control and quality assessment to ensure that you have high accuracy in doing the types of things you want to do. So the question, of course, from many people is how many annotations do I need for my training? Well, it depends. Here's a graph showing on the left the performance level going from 0 to 100, and then on the x-axis is the number of annotations in thousands. So it ranges from 0 to about 500,000 annotations. And the yellow line here represents a fairly simple case, probably similar to the camera shoot system I'm going to demonstrate to you, where you have a nice controlled environment. And here's another example. The blue line here probably represents a little more complexity, such as trying to identify catch events in a longline fishery. And the third line here, this is in a situation that has a lot of complexity. And this is going to be similar to the other tool I'm going to present to you is our stereo camera system. And here we're not only trying to measure the fish, but determining disposition of the fish, whether retained or discarded, but then also species identification. And so this is a very complex thing to do, and so it's going to require hundreds of thousands of annotations and a lot of feedback loops for quality control and validating what you're getting. So general guidelines for collecting training data sets. You need a sample of data from your problem that is representative of the problem you're trying to solve. This means that there needs to be enough data to reasonably capture the relationships that may exist between the input features, a species identification, for example, and the output features. So again, it depends on the complexity of the problem. Okay, the first tool I'm going to talk about is our camera shoot system, and here the application is accounting for halibut discarded in the Bering Sea trawl catches to reduce mortality. The idea here is to try to get the halibut sorted from the catch and get it back over the side. And our tool allows that to be done much more quickly because you don't have to have an observer sitting there sampling the fish for length, which we use for estimating the discard. Here's a picture of a camera shoot system. The big one in the back there, that's about 1 meter long, probably 60 centimeters high. And in the foreground, this is a smaller shoot system that can be used on smaller vessels to inspect whatever fish or invertebrates you can put beneath it. This is a very flexible tool in terms of design and can be pretty much made into any sort of system that you want on board a vessel. So this first video clip, I'm going to show you a deck crew sorting halibut from a trawler in the Bering Sea. The blue box that's straight below, that is the top of our camera shoot system. And you can see that halibut are being sorted from the other flatfish here. Typically, there'd be an observer here that would take the catch and measure length and also mortality. The next little video clip here, this is what it looks like from inside the camera shoot system. So a fish is slid through the system. The and the system identifies it as a fish, and then it takes a length measurement. Again, this can be any number of species, not just halibut. In 2015, our results showed that we had very good correspondence between the human measured lengths and the image measured fish, but only when those images were good. So the last 4 years, we put a lot of development work into prevent obtaining bad images, ensure that our measurements are improved, and also, very importantly, to detect poor images. Because if you have bad images, you just don't want to use it for trying to get a length measurement. For example, if the halibut is flopping up, it's going to be closer to the camera, and since it's a single camera system, we don't know how close it is, and so you don't want to try to estimate a length from that fish because it'll seem longer, and actually it's just closer to the camera. This next slide here, you'll see that through these improvements, we've gotten much better, and we're now providing very accurate real-time estimation of haul-specific discard on a haul-by-haul basis within a few minutes after the haul is finished. The XY plot on the left shows the correspondence between the estimated and the observer lengths, and the plot on the right is a length frequency histogram that shows that we have a very accurate correspondence in all of our lengths. The other thing we're developing for the camera shoot system is species identification. You can see the red lettering here donates the accuracy, and you can see that we're really high in accuracy for well over 50 species at this point. Even for some very hard to distinguish rockfish species that are even hard to tell the species with a fish in hand, including black spotted and rough-eyed rockfish, and then also short raker rockfish. So the camera shoot system certainly works very well for species identification for as long as you have a large enough training data set. But even for some of the lower training data sets, you can see that we're still getting pretty high accuracy. Next steps towards implementation for the camera shoot system is we're going to be deploying and have been deploying in 2019 algorithms to automate that length estimation in real time for halibut. We're going to continue to expand our species identification. We're out on a trawl survey in the Gulf this year, and we'll continue to automate the species ID in real time because we see that this could be a really important tool to support species composition, sampling, and length measurement for our observers out on vessels. The next thing we're working on about a year or so now is development of machine learning to develop detectors in salmon plants, and I'm going to show you a short clip of that next. Here we had a relatively small training data set, about 6,000 images with salmon in it. Here the idea, of course, is that you have to account for all the salmon that come into a plant, and so you ensure that they're all being accounted for. You can see our recall here is only about 70% right now, and so we're collecting much more data already on this and trying to improve it so it can be much more accurate. Obviously, if a salmon is below all the other fish, you can't see it, the detector is not going to see it, going to identify it. But we're finding is that even a small portion of the salmon is visible, we should have a pretty good chance of identifying that as a salmon. Maybe not necessarily a species, but it seems to be working pretty well. And this here was a truth of concept project we started last year, and again, this is collecting much more data this year and improving its accuracy. Okay, next I want to talk about our stereo camera system, and the red circle here, if you look at that, there's a vertical system, that's our stereo camera system, and the other system that's out on the stabilizer bar here is a standard system. We mount our cameras the same as everybody else looking back at the hauling station. Our objectives for stereo research is to track and measure all the fish captured at the rail, determine whether it was retained or discarded, and also species identification, because these are all the three elements that we have to do catch estimation. Obviously, working with this type of imagery where you don't have a controlled environment like in the camera shoot system poses many challenges. Some of those, of course, is deformation of the fish, so the fish are flopping all over the place, so if you can't see the entire fish, you can't get an accurate length measurement. Asynchronous images, both the left and right cameras have to be within a millisecond of each other to ensure accuracy. And one of our main challenges at first was environmental noise, especially the water surfaces, because you have to be able to identify when that fish comes out of the water immediately, because they're only going to be in view for a few seconds or fractions of seconds. And so this next video I'm going to show you here, this is solving that environmental complexity problem of having a wild sea surface moving up and down, and trying to identify where the fish starts and the fish stops. You'll see a line at the bottom of this video clip, and if you watch that, that's actually an outline of the water and the side of the ship. And if you look closely, you should be able to see when a fish is being caught. So this, again, this year I think was one of our major developments, and it now gives very accurate catch count in our process. Next, I'm going to show you a short clip for disposition. And so here, trying to determine what fish are kept and which fish are discarded. This turned out to be fairly easy in that you just need to know the directionality of the fish. So are they coming up or are they going down? If you look in the upper left-hand corner, if they discard fish within view of the camera, it'll also pick up fishes being discarded that are not on the line. Okay, this next little short video is going to show a 3D bounding box around each of the catch events here. And that's using the stereo cameras, because we need to know the depth of field so we can get an accurate length estimation, because they're not straight on the camera or flat on the bottom of like the camera shoot system. The numbers represent the length in centimeters. So I'll play this for you. And you can see it's such a really dynamic process, how much more difficult it is to get accurate length measurements. We've made a lot of improvements over the last year, and I think that we'll be able to solve this one here. And again, going through the development stages as we did with the camera shoot system, and that is identifying those photos where are bad photos that you can't get an accurate length measurement at all. Okay, next, here's a detector that we trained, and this is for counting hooks. And you can see that even for hooks, it does very well. Again, you see this imagery though is in nice and bright and excellent imagery. I'm uncertain how well that would work in the dark and that sort of thing. This again, this one here was a proof of concept. It's certainly going to be doable, but again, you may have to have ensure you have good lighting. So what's next? Here we want to distribute the knowledge and design of the systems that we've developed, and all of the imagery that we analyze in real time. So we want to provide that end-to-end solution. And so we put out systems, they collect the imagery and the sensor data, and then they're able to also send that information back home through the satellite network. We're also going to be providing access to open source machine learning algorithms to promote development and automation in other fisheries. And so these algorithms, although now trained towards Alaska fisheries, they can be retrained for other fisheries anywhere in the world. And finally, we want to provide access to the machine vision stereo camera software to promote automation and development of 3D vision systems. These systems are going to be required in an open air environment to estimate size and also estimate volume measurements from bins. We see a huge impact for machine learning. We think this automation is going to play a fundamental role because it provides a credible, cost-effective avenue to collect and analyze enormous amounts of data at the source itself. And so you no longer have to worry about hard drives filling up on vessels or storing all that data because it's going to be processed on board. With that, I'll end my talk. So thank you. And Mark, I believe you're up next.
Hi, hopefully everyone can hear me. I'm Mark Hager with the Gulf of Maine Research Institute, and I'm going to talk today about building efficiencies into some of the EM programs that I'm involved with. And I'm going to talk about some of our successes, our difficulties, and then some recommendations that I have for developing artificial intelligence into an EM program. And particularly today, I'm going to be talking about New England groundfish EM programs. And I want to start by saying that I am not an AI expert. I'm actually a fisheries monitoring guy that has been working on electronic monitoring for the last 7 years. So I've been doing everything from installations to video review to program design and policy work on electronic monitoring. And I have a big team and group of collaborators that have been working on the work that I'll be presenting today. So just real quickly, some of those collaborators are the fishing industry in New England, the Nature Conservancy, Maine Coast Fishermen's Association, Cape Cod Commercial Fishermen's Alliance, EcoTrust Canada, Team Fish, Snap IT, Integrated Monitoring, and then Seavision AI, who's been helping us with a lot of our automation. This work has been funded extensively by the National Fish and Wildlife Foundation. So to start, just want to give a little bit of a fisheries background. We're talking about New England groundfish. The technical name is Northeast multi-species. They have 4 major gear types: trawl, gillnet, longline, and jig. There's about 200 active boats, give or take. There's 13 different species that are regulated in the fishery, made up of mostly roundfish and flatfish. So that's the roundfish are cod, haddock, and pollock, and then the flatfish are an array of flounders. It's managed by a sector catch share program, so vessels are fishing quota. And to set the stage a little bit, the fishery is in relatively poor economic condition. In 2012, it was deemed an economic disaster due to a continued cut in quota, year after year of cuts. And that's really why the Gulf of Maine Research Institute got into electronic monitoring. We saw that the industry needed some economic relief, and monitoring was one of the bigger costs they were bearing. So we wanted to see if we could make it a bit more affordable. And while it is affordable, and it can be, you know, a reasonable substitute to human observers, we saw that we could probably make it much more affordable if we applied some really smart technology. So we looked into collaborating with a couple groups to start to drive artificial intelligence into our programs. So I'll start briefly by just describing the 2 programs. There's a ton of details that go into these programs, but I just wanted to kind of cite the main differences, especially when you're thinking about artificial intelligence. So we have an audit program and a maximized retention program. In an audit program, in that program, the fish are being, every fish that is going to be discarded that is a regulated fish is being placed on a measuring strip before it's thrown overboard. So it's really, really detailed fish by fish accounting, and then that is used to validate a captain's log. In another project, the Maximized Retention Program, all the fish are actually landed, and instead of using EM for that detailed accounting, the EM is used just to make sure that the vessel is complying with the landing rule. And there's also a dockside monitoring component in that program, and that's where the majority of the data will be collected. So I want to talk a little bit about where we focused AI and why. I'm going to play this little video while I talk about it. So there's a video from the audit project. And as you can see, there's quite a bit of fish getting dumped. There was dumped into a checker pen there. It's highlighted in green. And they sort through those fish, often one by one. So it's quite a bit of video review to be done there. And that's where we really decided we were going to start focusing our attention was on video review and video processing. And the main reason was budget. We're looking to see if we can make this more affordable. And in some of our programs, we've seen the budget account for up to 50% of the total program costs. So that was a very big driver. The other piece was time. Trips can take, depending on the program, 12 or more hours to review on a single day trip. So that's pretty time consuming. And there's a lot of stakeholders that in the future and even now we'll be looking to have pretty quick data turnaround, especially if you're doing in-season fisheries management. And especially as things start to scale up, it's not too big of a problem if you have a team of a couple of reviewers and 1 to 2 trips coming in a week. But if you have a team of a couple of reviewers and 100 trips coming in, that 12 hours can get pretty onerous. And then some of the other items, I'm calling them trickle-down effects that have been, they're kind of secondary, but they're really, really important. Reasons we decided to focus AI on the video review portion. Data transmission, data storage, and data quality. And what I want to focus on here is if you think about operating these on the edge, what I mean on the edge is if you're operating AI actually on the vessel, these things start to become very powerful. For example, with data transmission, if you can actually operate some artificial intelligence to eliminate white space or measure some fish on the vessel and then either send back less video or send back just analog data, you could really, really lower your transmission costs and make wireless transmission really viable. We've already seen in some of our programs that it is viable, but it becomes much more affordable and you can do it a lot quicker. Just like that, data storage as well becomes much less expensive. The less data you collect or the less data you transmit back to shore, the less data you would have to store. And then one that often gets kind of forgotten about AI is data quality. And what I mean there is that you can actually start to measure the results or the performance of an algorithm. Unlike if you have human review happening, sometimes it's tough to evaluate from reviewer to reviewer. But an algorithm can provide metrics, evaluation, or a score of how it was performing, and you can use that to evaluate the quality of the data that's being output. And the video there was just trying to show that. As I'll show you here again, we have video reviewers actually measuring each one of these fish. So it's pretty tedious. So that was one of the main objectives we were trying to automate. So talk about some successes. First, the audit project. We focused on species ID, species count, and species length. And that was because we had really detailed data collection happening in that project. So we really wanted to try and solve that problem, crack that nut. And what we started with is object detection, object recognition, and then object tracking. So the object detection was, where is there an object? And then object recognition was, is it a fish? What species of fish? And then object tracking really helped us make sure when we were counting the fish, because this program has a counting component to it, that we weren't double counting fish. And those algorithms were developed from a driven data competition. You can see the partners on top of the image there. Driven Data, the Nature Conservancy, the Data Branch, and Sea Vision AI worked. They ran a data science competition that created the base algorithm that then was handed off to Sea Vision and put into a container for our EM vendor to begin to utilize to try and put that into our EM workflow and start to create a workflow where we have assisted human review, where some of the species identification, lengthing, and counting would be happening from the AI instead of a person going through each fish. On the other hand, on the match retention project, we took a different approach. We didn't have the kind of detailed fish counting one by one as we do in the audit project. So we focused on trying to reduce some of the white noise in a fishing trip. And what I mean by white noise is steam time or downtime or time when there's no one on deck and they're just moving to a new area. So we focused on activity recognition opposed to object recognition. And we're looking, so in activity recognition, we're looking at the scene more as a whole. And we tried to figure out if we could automate the video to denote net handling, fish sorting, hold loading, and offloading. And you can see in the little chart below that we've had some really good success at doing that. The top lines there, the colored lines, represent how sure the algorithm is that event was happening, and as it gets towards that second gray line, that's a very high confidence that it is occurring. And the bottom lines are our video reviewers continually inputting what they see and retraining and improving the algorithm. So that's kind of the process we're in there now. And so for these two projects, we took different approaches because we had different training data sets. For the audit project, we had a lot. We had 5 years of measuring fish, humans watching video and measuring fish. So we were able to use that data set to build the AI to measure and ID the fish. A nice annotated data set existed. With the Maximize Retention project, it was much newer. We didn't have that data set. So from the onset of the project, we actually built into our video review annotations that we knew would be helpful down the line to develop some of the AI. And one like tidbit you can see from both of these images is on the left-hand side with the audit project, you're really looking pretty straight down on that fish, and that was by design. That was our recommendation from C-Vision AI, who helped us on these projects extensively. And then again, C-Vision helped us on the right-hand project with the max retention. And although it's a very different application of EM, it's much more zoomed out. It's looking at the whole deck. It's also looking straight down. And the point there is so that you have a really good view on the stern when a fish breaks the plane from the boat to the water being tossed overboard. All right, so I'll get into a couple of the challenges. We had a handful of challenges. I'll talk about some developmental challenges and then move into some of the ongoing challenges. So access to training data, I already mentioned that. It's pretty critical that you have good data to start with. And in the audit project, we are very fortunate that we had many years of good training data. But then you still have to access that. You have to have permission to access it, and then you physically have to hand it over to whoever's actually building the AI. And those obstacles shouldn't be overlooked. In the Maximize Retention project, we actually had to build our own training data. So we did that from the onset. We knew we were going to want to do this, so we started collecting it right off the bat. Another challenge was determining the correct architecture or the code framework. This is something we relied heavily on our AI contractors to do. So there's a lot of algorithms out there that exist, and they can be adapted. Choosing the one that was going to be the right tool for our needs took some expertise. And the way we did it is we picked a very simple tool that already existed and then adapted it and made it a bit more complex to suit our needs. And then development budget. AI is pretty expensive to build, and unlike putting cameras on a boat and recording video, you have immediate results right off the bat. You get video in, and you can start watching that. That's relatively easy to get budget for, but getting budget for something that's going to have potentially show some gains 2, 3, 4, 5 years down the line can be a bit more challenging. And then some of the continued challenges that we're dealing with now, I have operationalized. So a lot of what we've done is somewhere between proof of concept and being ready to actually use. So we're in the stage of trying to operationalize it. So for some of these algorithms, for the activity recognition, we have it working really well on 2 to 3 boats. It's not ready yet to be broadly applied to a fleet where there's going to be a whole bunch of different characteristics of lighting, of boat size, of boat setup, of different species. So there's a fair bit of work to go from, you have a proof of concept pilot to actually an operational AI setup. And part of that is integrating it into the vendor workflow. So you always have an EM vendor working on these projects, and you really need to be sure that you're communicating with the vendor well and planning with them on how that the AI that you build is actually going to work within their workflow, and make sure you're building something that they actually want to use. Another continued challenge is operating on the edge. This is a challenge, but also a huge opportunity. Operating on the edge is thinking about actually moving the AI to the ship. So when you're doing the processing on the ship, right now, all of our processing is happening back in the lab, either at GMRI or at one of our vendors' compute environments. And one of the big challenges for operating on the edge, one of the biggest challenges used to be, the form factor or the technology or the compute power. And we're starting to see that kind of go by the wayside, and the technology is available. More what we're seeing now is trying to figure out what's acceptable, kind of goes towards my last bullet here. What's acceptable or what's good enough? A lot of people say, AI can do this, AI can do that. I can ID fish up to 95%. Is that good enough? And what is going to be accepted in federal policy? That's a pretty big question that I don't know the answer to, and I think there's a fair amount of people that are also kind of starting to think about that question. And GMRI is actually going to be setting up a workshop early in 2020 to begin that conversation around what are some of the standards for integrating AI into an EM program. What does that look like? So I will close with some recommendations, and this is just kind of for me, my experience on working to kind of coordinate the pieces of AI into an EM program. So one place I want to start with is you want to start where you have data, because if you don't have data, it's really going to be pretty much impossible to build AI. And it's not just data; it needs to be structured or annotated data. You need imagery that some process has gone through and it's actually been organized in a manner, or it's been labeled in a manner. So we were really lucky in our audit project where we were able to have 5 years of that. So we really got a nice jump start there. And I wanted to put a shout out if you are in a position where you need data, or if you have data that you'd like to supply for common use and research and development. The Nature Conservancy has a program called www.fishnet.ai, and that is an open library where they're encouraging people to contribute and to utilize imagery that is labeled for fisheries monitoring, so you can actually build AI. So I encourage you to visit that website if you either need data or you have data you want to share. Next, focus on your workflow and your pinch points, not what's neat or cool. A lot of times people want to focus on what's really cool, because AI can do a lot of great stuff. A friend of mine last week asked if I was involved in the face aging app, or whatever that thing is. And while that would be really cool to see what a fish looks like in 30 years, it really wouldn't do anything for us. So we focused on how to reduce video review time, because we knew we would see big gains in our program bottom line there. So focus on your program's workflows. And then work with your vendor to integrate it. Work with the EM vendor that is, running your program or involved in your program, and consider interoperability up front. It's really important to work with the vendor, but I would encourage not getting, stuck down at one line with a vendor. If you can create a tool that could be broadly applicable to a variety of vendors, you'll probably create a really competitive and compelling environment for more and more innovation in your fisheries monitoring. I would say consider AI in the program design, thinking about it ahead of time, kind of like we had the ability to do in our Maximize Retention program. We knew we were going to want to do it, so we built in some of these annotations into our program design in our video review. There's other ways you can do that too. You can start to think a little bit outside the box. Right now, there's certain ways of doing things in EM, and that might always not be the way it needs to be done. So for example, around the country, folks are trying to trend away from watching 100% video review. The lower amount of video you can watch for a lot of the industry seems like the better route. It's going to be cheaper. But as AI, if you have a very simple application for AI and you could watch video at a very cheap price, it might actually be a value add to watch all of the video using AI, and then you're actually getting to more of a census instead of a subsample, and then your data set, actually your data output, might be more valuable to you. So thinking outside the box and not staying within the same boundaries that we started with fisheries monitoring and electronic monitoring before AI came into the picture. I would encourage that. And then consider AI-assisted review. So, you know, definitely a lot of folks think you get a hard drive off the boat and you plug it into a machine in the lab and it just processes it all and it tells you you have 10 cod and 7 haddock. That's not exactly what we're aiming to do at the moment. Maybe down the line, that sounds great. But what we're trying to do is use the AI to assist our human reviewers to make them more efficient at their job. So let the AI do what it does well, and let the skilled, trained humans do what they can do. And then lastly, I would just recommend to have realistic expectations and timelines. We've had a lot of people working on this, and a fair amount of money, a lot of effort has gone into it, and we have really accomplished some really awesome things. Some really impressive AI has been developed, but I still feel like we're a good way away from broad fleet implementation, where we're going to see the very large gains that everyone wants to see. So just setting your expectations ahead of time and in your timelines ahead of time. And once again, I mentioned it earlier, but just considering how policy is going to play into it and what is going to be accepted from whoever your end users are. And if you're building AI, just making sure that you're realistic and realize if they're going to be able to approve it in the first year you develop it, or if it's going to take a couple of years, and you might need to build up a little bit of a comfort factor there. So with that, I think I will close, and I want to just thank Brett for setting the stage. That was really great, Brett, and Farron for his highly technical presentation from Alaska, and hope you enjoyed my less technical, but more programmatic overview of our experience implementing artificial intelligence into electronic monitoring in New England. Thanks.
Thanks a lot, Mark. 5 minutes after we started this webinar, the Navy's Blue Angels started practicing making flight runs over my home office. So hopefully that's not going to cause any difficulties here. I'll try to be careful of my mute button. We do have a few questions. One or two of them I think got answered during your presentation, so I may skip over one or two of these and then ask the questioners if they'd like to follow up. Do that with these guys later, and we'll provide their email addresses. Here's a question. Well, I think we can get pretty quickly. Are the software algorithms currently available? I'm not sure if that one was for you, Mark, or for you, Farron.
Yeah, I can probably start on that one. No, they're not. So the idea here is that those will be put on GitHub, probably starting late this fall, or late in 2019 or early 2020. And so what a person could do who knows how to develop AI, they'd be able to take that detector and retrain it for their specific fishery.
Yes, and for our programs, we have a couple different programs and we have a couple different contract setups when we did the development. So some are and some are not. So if you are interested, at the end of the webinar, well, actually you can see it there now. My information is up there. Feel free to email me and ask specifically, and we can start the conversation there.
Great. Here's one for you, Mark. You mentioned that you've had some success with data transmission. Can you elaborate on this? Wi-Fi or cellular? How much data transmitted, and what was the cost? Is there any concern that transmission costs will simply replace the current expense incurred through data review?
Yeah, so we've had some really good success. We have transmitted, last time I checked, it was about 120 trips in our Maximize Retention project over cellular. That's the process we're using right now. And the cost was a flat rate. I'm unsure if that is proprietary information for that particular vendor, but the cost, it's not astronomical. It is substantial. One of the trickiest things about the wireless transmission is we had a couple of vessels that do very quick turnaround trips. They come into port and they turn around right away. And being able to get the information off the vessel quick enough was an original challenge, but we have overcome that. The cost of transmitting the data, if you were to pull all raw imagery from the vessel would probably be astronomical. I think where our vendor has really excelled is crunching that data into manageable sizes and transmitting that off the vessel.
Okay, great. Thanks, Mark.
Yep.
So that's all the questions that I have currently up on the screen, and we have a few more minutes left, just, well, 4 or 5 more minutes left in our webinar. But Brett, I think you might have had 1 or 2 questions teed up. Is that correct?
I'll
Yeah,
say,
go ahead, Mark.
if you want more information on the wireless transmission, there was an EM information article we put out a couple months back on that. If that doesn't satisfy your needs, feel free to reach out to me, and I'm sure we can get you some more details on that.
Yeah, just really quickly, I want to save more time for people on the phone, but my question at the time was for Farron or Mark, was just being able to adjust how gear is set up on vessels to mesh better with AI development. In other words, could you start to develop colored lines, colored gear type, colored hooks to better support the data collection that may be different than traditional gear setup?
Yeah, I can certainly speak to that. Yeah, so again, if you recall my chart on complexity, and so anything you can do to reduce the complexity of the environmental situation or colors, let's say that all your hooks are green, it's going to be much more easy to develop an algorithm that'll identify green hooks unless there are a dozen different colors. So yeah, I mean you can do it, but it's going to the more complex the situation, the bigger the cost of developing the detector, because the larger the training data sets that you need, and then also the larger the validation will also be much more take much more time.
Yeah, similarly in our efforts, I often ask Ben Woodward from C-Vision AI, who we work really closely with, could we make this easier if we painted the deck white, or if we used colored totes, or if we asked fishermen to run all of X, Y, and Z species over a conveyor? And every time the answer is yes. You can really make the job, the development job, and the job that you're trying to task the artificial intelligence with much easier with some simple on-the-deck operational type adjustments.
Yeah, I can add to that too, is that if you can have colors that are really contrasty, it makes it much easier for the detection. And so you don't want to have the white side of a halibut coming up alongside of the white side of a boat, because it's going to be very difficult to detect.
Thanks, Farron. I'm pulling up another question here. Hang on. Farron, can you outline the goals for the stereo camera project as it relates to larger implementation of this technology? I.e., if the technology is proven to be viable, how will it find its way into existing or new EM programs in the U.S.? Is the expectation that private EM companies will incorporate this into their technology?
So sort of a multi-layered question there, I guess. So I can tell you what we're doing in Alaska is that starting this next fishing season is that for the first time we'll be, at least for the longline fishery, putting in several servers in the various ports to process the data in port in near real time. So as soon as somebody completes the trip, the data are processed, and then the analysis then of the results then will come back to our data set there at Alaska Fishery Science Center. So that's a step closer to where we want to get to is edge computing. And NOAA Fisheries is not interested in competing with any providers out there. What we're interested in is having the providers start thinking about how they can start using these algorithms and incorporating them into their own systems. The system design that we have, that's going to be available again sort of towards the end of 2019. And so the fisherman wants to develop his own system. There'll be information there where he could put his own stereo system together. And one of the reasons for us doing that is that then anybody out there, any EM provider, can develop their own stereo camera system, and they don't have to do all the research of how to put one together. And the processing application of that goes with the stereo cameras is also going to be provided for free. And so again, we're just opening up the doors for any private companies out there to start going to the next level.
Okay, thanks a lot, Farron. It looks like we did get several more questions in there towards the end. We're not going to get to them on this call, so I'm going to make sure that, well, first, if you asked one of those questions that we didn't get to, please direct it using the email addresses on the screen. Please direct it to our panelists as appropriate, and I'll make sure that our panelists also receive these questions that came across, just so you know, okay? So thank you for your patience on that. We'd like to thank those organizations that support EM Info. They're listed on your screen. A couple of really quick notes here. If you're not yet receiving our monthly EM Info update emails, there's a place to subscribe to those at eminformation.com. Also, if your work connects with this field in any way, and it probably does since you're on this webinar, we invite you to join our directory of practitioners on the website. You can find that there. It's an easy way. It's an easy sign up, just a way to let people know about you and your work, knit this community together a little bit more, and let people get in touch with you directly if they'd like to. We'll have a link to this webinar up by tomorrow, and we'll share that out across Twitter and across our next update as well. So we've taken about 1 minute over, but that's not too bad. Thanks again to our presenters and all of you for joining us. We hope this has been an hour well spent, and we'll see you next time. Thanks a lot.
Thank you.